Okay, good morning again. So, this is our final week of classes, and we are going to finish chapter 6. Uh, so, we are going to continue from where we left off. We were talking about stochastic random variables, which change over time. So, and we are going to specifically focus in this chapter, section 6.2, we are going to focus on Markov chains, which are discrete time, discrete state Markov processes, which mean that there are random variables take some finite discrete values, and the time steps are also discrete. We have some the time steps like at time 0, at time 1, at time 2. It goes on like this at discrete time steps. These may be day 1, day 2, day 3. So it may correspond to days, it may correspond to number of tries. But in any case, we can jump from one time step to another time step, and we will analyze these transitions between different time steps, to transition from the current time step to the time step that are h, for example, time steps further, not necessarily adjacent. When we think about a Markov chain, this all of these they become x0 becomes a random variable. Okay, this one here uh, is not a specific scalar value. It's a random variable at time 0, which I'm going to show you some examples. It may be one of any one of the possible states with certain probabilities. So there's a probability mass function over the set of states at time 0. Let me also change the mouse pointer size. All right, so uh, for example, x0 may indicate the weather condition at the beginning of our stochastic simulation, stochastic analysis. At day 0, first day may be 60% rainy, 40% sunny. For example, imagine we have a random variable which can get one of the two states, rainy or sunny. And being not observed anything when you say something like that. For example, day 0 may be 60% sun, rainy and 40% sunny. The random variable here can be one of those two states, and we don't know for sure what it is. And then we are going to have transition probabilities between adjacent time points that tells you if you were, for example, in sunny state in the at day t, for example, at day t plus 1, what is the probability that you will remain at the sunny state, or what is the probability that you will go to the rainy state? So we will have transition probabilities between states that shows one step transition probabilities will be between two consecutive time points, and with that we'll be able to answer different questions. And we will at the end, what happens, for example, at day 10 is going to be another probability mass function. It's going to be, we are not going to say it's for sure it's going to be sunny at day 10. It may be, for example, depending on the transition probabilities, of course, but what will most probably happen at the day 10 is going to be another distribution probability mass function over the set of states. Here, remember the Markov property when we talked about the Markov processes. The property implies that the distribution of xt plus 1. This when we say can be predicted, we are not predicting a single state. All those states will still have some probabilities. When we say xt plus 1 can be predicted, we are still talking about the probability distribution over the set of states at t plus 1. I think this will be, all these abstract things will be best explained with an example, this sunny rainy example. Actually, we have such an example in the book. Let me go ahead and find that one in the book, which is, I think, This one. This is again sunny, rainy, the same example. Let's look at this example 6.7, which is really nice. It shows all the things we are going to discuss in a couple of minutes as well. So look at this example. In some town, each day is either sunny or rainy, which means that we are going to have a random variable with two states. And in these in this chapters, when we are analyzing stochastic random variables, we are looking at a particular property, the weather condition in a day, for example. We are not, these states do not mean that we look at different variables at every time point. The variable is still the same. It's the weather condition. But the only thing is that that weather condition now has a time attached to it. Weather condition at day 0, day 1, day 2. Okay? So our random variable x here shows the weather condition in a town. Okay? And when we attach a time to it, it shows the weather condition in a specific day. And this, when I say it shows the specific condition in a specific day, I'm not thinking about a specific state. When you observe that, for example, you may say that x1 may be sunny. Okay, this is your observation, may be that. But when you think about x1 itself like this, it's a random variable, just like the other random variables we have discussed up to this point in this semester. It may be, for example, x1 may be a random variable whose PMF may be something like this. It's rainy with probability 0.6 and sunny with probability 0.4. Okay, so this is what x1 may be. So let's take a look at the example and proceed according to the values provided in the example. And I will give I will ask some other questions related to this example too. So here, let's see what the information given to us is. A sunny day is followed by another sunny day with probability 0.7. So this 0.7 is a transition probability from one state to the other. And since, look, if you look at this sentence, it's not, doesn't specify a specific day. For example, when it say from day 5 to day 6, following a sunny day, a sunny day followed by a sunny day is probability 0.7, but maybe at day 7 to 8 it may be different. In such cases, when the transition probability is different from specific day to day, we call such Markov chains non-homogeneous. Okay, so in an homogeneous Markov chain, the transition probabilities are specified globally over all consecutive time points. So as you can see, the sentence is something general. It says a sunny day is followed by another sunny day with probability t1. So for any t, the probability that xt plus 1 is equal to sunny, given that oh sorry, I should have written not t plus 1, so this should be probability, okay, and this should be xt plus 1 is equal to sunny, given that xt is equal to sunny. So now given that today is sunny, or at t it's sunny, the probability that it will be sunny at t plus 1 is 0.7. So what is given to us in that sentence is this, and this is for all t. Okay, for all t, this probability is given to us as a transition probability from sunny state to another sunny state. A rainy day is followed by a sunny day with probability 0.4. Okay, now a rainy day is followed by a sunny day. So given that today is rainy, let me get back to this one. Is equal to sunny, given that today is rainy. Right? Was this information that was given to us? Given that today is rainy, so this should be equality net. Let me just correct that. Xt is equal to rainy like this. Let's take a look at the book again. Uh, Rainy day followed by a sunny day with 0.4. Okay, so uh, again for all t. These are the only transition probabilities that are given to us. Let me ask you, what about the other transitions? What about if today is sunny, what is the probability that t plus 1 is going to be rainy? It's not given in the question. How are we going to find those? So specifically, what is xt plus 1 is equal to rainy, given that xt is equal to sunny? Exactly. We are going to use the complement rule, because since this has only two states, a variable can be, exhausted by using the complement rule. If it's not sunny, it's going to be rainy. So the probability that it's not going to be sunny is going to be 0.3, which is this one. So given that it's sunny, the probability that it's going to be rainy is 0.3. Similarly, given that today is rainy, the probability that tomorrow is also going to be rainy. So given that today is rainy, is 0.6. Now I have all the transition probabilities. So instead of writing all these probabilities with these conditional probabilities like this, a better way to show this is as a table. Okay, so if I have this rainy, sunny, if these are my states, and if I have n states, I may have an n by n matrix that tells me from rainy to rainy it's 0.6, from rainy to sunny it's 0.4, from sunny to rainy it's 0.3 and 0.7. As you can see, each row adds up to 1, and this shows the rows and columns have certain semantics. So given that today is sunny, the probability that, so given that today is a row in this entry ij is showing that given that today is some state I, what is the probability that tomorrow is going to be j? Okay, so it's going to, it's showing us that probability. Okay, so these are called one-step transition probabilities. Let's see what the question, what the example is asking us about. It rains on Monday. Make forecast for Tuesday, Wednesday, and Thursday. Now, we are the first day here is fixed. We know that. Let's call these Monday, Tuesday, Wednesday, and Thursday 1, 2, 3, 4. So we know that at t is equal to 1, for example, we know that x1 is rainy. Okay, this is known. Now, what about x2? Okay, by just looking at this, you immediately can say that Tuesday is going to be 60% rainy, 40% sunny. Okay, but what about the interesting thing is going to happen at x3? What about x3? What is the probability? For example, can we say x3? Can we use one of these values here to determine the probability of rainy or sunny? What we should actually do is we should consider all the possibilities x2 can have. X2 can be, so x2 will be rainy with 0.6 probability, and it's going to be sunny with 0.4 probability. So it's going to be rainy. If it's going to be rainy, it can again be rainy with 0.36 probability. But it could be sunny and then rainy. So what we need to do is the probability that it's going to be rainy in day 3 is going to be 0.6 times 0.6. Okay, if Tuesday is rainy and then Wednesday is rainy, yeah, exactly, it's going to be like a tree. And it's going to exponentially go all of it, all the possibilities. And the tree actually is happening by all these conditional probabilities that we compute. It's just, again, so it's here, this is for Wednesday. This is exactly doing what I told you to do. So this is trying to predict what is going to be sunny, and rainy could be done similarly. So it's going to be, we are going to just, again, using the complement rule to just for example, the probability that it's going to be rainy is simply going to be equal to 0.6 times 0.6 plus, it could be sunny too, right? It could be sunny with 0.4 probability. If it's sunny, it will be followed by a rainy day with 0.3 probability. So it's going to be this, which is 0.12, 0.36, 0.48. And the probability that it's going to be sunny should be the complement of this, which should be 0.52, which should be the one that is computed in the book. Yeah, it's 0.52. As you can see, it used the it found 52 by multiplying and summing up different values. Okay, now if we ask what will happen in day 10, computing it like this is going to be really difficult, right? I mean, if I tell you x1 is equal to rainy, and if I give you that same matrix, 0.6, 0.4, and the others were 0.3 and 0.7. If I give you this matrix, rainy, sunny, let's see, if I ask you what's the weather is going to be like at 10, okay, at day is equal to 10, what is the probability that x10 is equal to rainy? Okay, let me ask you this. So as you can see, since it's like a tree, all the possibilities that we can have in between exponentially increases. I mean, if you just have two states, it will be like you have to look at two, since day one was fixed, you should look at 2 to the 9 possibilities. So it could be, for example, the first day was rainy, and then it could be all rainy until day 10. And it could be rainy, sunny and rainy. And then it's basically you're going to, if these rainy and sunnies are 2 bits, zeros and ones, since they could be anything, you would have 2 to the 9 different values from day 2 to day 10. I mean, if you consider day 10 also to be sunny. So you have to look at all these possibilities. And this particular instance, for example, what is the probability, if I ask you this, what is the probability that all 10 days are rainy? It would be easy to compute this, right? You know, the transition from rainy to rainy is 0.6. There will be 9 transitions. We know that the first day is rainy, that was fixed. So in order for all the following 9 days to be rainy, the probability of that event is 0.6 to the power 9. You have to have that many transitions. So you have to add up all these different 2 to the 9 different cases in which you end up with a rainy day. So it may get complicated to compute it like this. There is actually an easier way to do that, which is, for example, in the Markov models, which uses try to compute probabilities similar to that. We're not going to talk about them, but there are, for example, dynamic programming techniques to utilize the recursive nature of the problem. I mean, the subdividability of the problem into different portions. For example, if somebody gives you what the probability up to a certain point, for example, the probability that if somebody gives you that the probability of rainy at day 9 is this, and then you can recursively compute what day 10 is going to be like. But what we're going to, it could be also done iteratively, and here's what we are going to see next. You see this transition probability matrix? If you take the powers, successive powers of this matrix, it would give you, for example, if you take the hth power of this matrix, it will give you the h step transition probability. So if I wonder what will happen in 9 steps from now, so it's going to be like t is equal to 1. I wonder what will happen at 1 plus 9. Okay, in 9 steps I will be at day 10. What will happen in 9 steps? What you could do is you could take the ninth power of this matrix, and the values in that matrix, the transition probabilities will directly tell you what the 9-step transition probability from every one of these days. So if you know that it's raining today, you can just multiply it with 1, 0, which will just take this first column. Actually, you cannot multiply it with, so this is a 1 by, yeah, you can multiply it 1 by 2, 2 by 2. So you'll multiply it with something like this. Let's see what will happen. I think I did the multiplication wrong, but the h-step transition probabilities will give us what will happen in those steps. And you can actually compute the 8 power of this by in log h time, right? You don't need to spend OH time. Taking the powers of something, for example, in order to, if you have this matrix, for example, if you want to take its 8 power, if you have 2 versions of the 4th power, okay, if you multiply it with itself in one step, you can find its 8 power. So which means that you can just by dividing it to every time, you can store these intermediate results somewhere, and all you need to do is take the square. So so if it's, for example, a very easy thing to do is, if h is an even number, a to the h is equal to a to the h divided by 2, a to the h divided by 2. So you have to only need to make a recursive call to h divided by 2 once, store the result someplace, and multiplying a matrix with itself could be done. And I mean, not all one time, of course. The number of states come into picture here, but you don't need to do in its 8 steps. So if it's an even number, it's like this. If it's an odd number, you can, after multiplying it with this, you may multiply it with another a to make it to find the result. I mean, these are integer divisions. I have here h over 2. If h is an odd number, okay, like 9, they will be 4 and 4. So a to the 4 times a to the 4 times some a single a will give you a to the h. So in log h time, all log h, and maybe also add n square here, where n is, you can, what is the matrix multiplication time? It's not n squared, it's n cubed, right? If it's not a sparse matrix, you can multiply 2 matrices of size n by 2n by m matrices could be multiplied with in n cubed time, I think. But if the number of states is really small, you can ignore this part if you're looking for very large step, far ahead step probabilities. So actually let's go over the slides too. So by and for Thursday forecast, we need to do 3-step transition probabilities, and it will be more difficult to do. Okay, but since we know what we have in day 2, okay, we have given that we know what Wednesday is going to be like, we can use that to actually, exactly, it uses that to find what will happen on Thursday. So, and here is usually, instead of representing the transition probabilities in a matrix or as conditional probabilities, we can also represent them as a graph, where every state is represented as a node in this graph, and the transition between states are represented as weighted arcs, weighted edges from weighted and directed edges. The weights are probabilities between these states. So the one-step transition probabilities may be represented as a graph like this, which is called a transition diagram. Now, here's something different. What if we don't know how what Monday is going to be like? What if we don't know whether it's going to be rainy or not? We only have a probability, okay, about being rainy. And it doesn't matter actually, just like we did the analysis for Wednesday to Thursday. Even if we don't know what when Monday is going to be like for certain, we can make a prediction for Tuesday by using 0.8 by using these two probabilities. Okay, if it's rainy on Monday, Tuesday is going to be rainy with 0.8 times 0.6 and plus 0.2 times 0.3. Okay, so this one, if Monday is rainy, the probability that Tuesday is going to be rainy too. If Tuesday is sunny, the probability that if Monday is sunny with 0.2 probability, uh, Tuesday is still going to be rainy with 0.3 probability. So if you add up these two things, you can find what Tuesday is going to be like. Okay, so uh, yeah, we can, for Tuesday we get this one, as you can see. And now, yeah, let's go to the slides now. Okay, so the transition probability, we have given one-step transition probabilities. They are indicated by this small p, lowercase p, Pijt, which shows the probability to transition from I to j at time step t. And if this is not dependent on t, for any t, if this holds, we just drop this t from this Pij function. The Pij will be constant for all t, as we have solved in these questions. In that case, we are going to have a homogeneous, that's kind of a Markov chain is called homogeneous Markov chain. These transition probabilities do not change from time to time. The states change from time to time. We have transition probabilities between states, but the probabilities that are given to us are general. They don't depend on time. Such kind of Markov chains are called homogeneous Markov chains. And the H-step transition probability is indicated with a superscript in parentheses. Tells you the probability to go from state I to state j. So given that xt is state I, what is the probability that at t plus h we are going to be at state j? So that's called an H-step transition probability. I mentioned homogeneity, which is if those transition probabilities are given to you generally, it must be a homogeneous Markov chain. If you ask, how can we know whether it's homogeneous or not? It should be given in the question. Depending on how the transition probabilities are given to you, it will indicate whether the Markov chain is homogeneous or not. And in this course, we're just going to focus on homogeneous Markov chains. We are not going to consider the other ones. All right. So the thing that will be given to us are going to be one-step transition probabilities, and I indicated on this matrix here. We can have an m by m matrix to represent those transition probabilities. Now, the state distribution, which I call probability mass function or probability distribution over states, indicates your current belief at what that random variable is going to be at that particular time point. And it's a random variable. Sometimes that random variable is called, the possible values that random variable can take and the associated probabilities are called state distribution. So this state distribution is nothing different than the probability mass function. Actually, it's, as the slides say, it's a probability mass function that shows the likelihood of outcomes and states at that time point. So this probability mass function is indicated with this capital P. So lots of terms coming up in here. This xt is the random variable, and its probability mass function at time t is indicated at pt, which can be represented as a vector. Okay, for example, if I ask you this, if I tell you, for example, when I say P0 is equal to 0.6 and 0.4, and knowing that the first entry shows, oh yeah, actually I did the multiplication incorrectly before, so I should take this one and multiply it with the first row, yeah. I mean, if this is 0, it will be all this value multiplied with the first column. So yeah, so let's see, for example, let's see what will happen. So this is P0. When I say P0 and this indicates rainy and sunny, as you can see, it's like a row vector, and it's a PMF, it's a probability mass function. The state distribution tells me it's 0.6% rainy, 0.4% sunny. So it's like a this state distribution is a random variable state. It shows the random variable state, our belief in that random variable at that particular time point. Okay, and given this, in order to find P1, for example, or given PT, in order to find PT plus 1, P1 could be found by multiplying P0 with that the capital P. Again, another capital with not subscripted. So these P's all are, I mean, this is like italic PT. We had just 2 slides before, we also named the transition probability matrix. Actually, we didn't say it yet there. So this is the probability mass function, and this is the state distribution at time H. Yeah, this is called P here in the book too. So this matrix, the one-step transition probabilities matrix, is also called P without with no subscript. Okay, so it may be confusing when we don't have the subscript. This P may indicate the one-state transition probabilities. So what I'm going to write here is the correct. So if this P is given to you as 0 0.6, 0 0.4, 0 0.3, and 0 0.7. These are our transition, one-step transition probabilities. If you multiply P0 with P, you're going to get P1. Okay, then if you want to find P2, all you need to do is multiply P2 with P1 times P. It will get you P2. If you want to get P3, you may multiply P2 with this one-step transition probabilities. It will give you P3. So let's try this, for example, multiplying 0 0.6, 0 0.4. If it's 0 0.6, the chance of rain is 0 0.6 at a day, and 0.44 being sunny in a day. This was the same thing for Tuesday, right? When Monday was, look at this, it's the same as the first row. If Monday was for sure rainy, this was our belief for Tuesday. So this was like P Tuesday. Okay, now what I'm saying is that P Wednesday could be found by doing a matrix multiplication, multiplying this thing with this one, and 0 0.3, 0 0.7. So how do we multiply it? We take this. So the result will be another 2 by 1 matrix. So the first entry will be 0 0.6 times 0 0.6 plus 0 0.4 times 0 0.3. Familiar, right? That's the probability of being rainy. We computed 0 0.6, 0 0.6. So we take this first row and multiply it with the first column of this one and add the individual multiplications like this, 0 0.3. And the second entry will be 0 0.6 times 0 0.4 plus 0 0.4 times 0 0.7, which should be, so this is 24, this should give you 52, all right? So one thing that you realize from here is that when I say, for example, P4 is going to be equal to P3 P, what we could do is we could actually write P4 as P3 could be replaced with this entity here, which will give you P2 times P times P. And this P2 could be replaced with what we have here, and P1 could be replaced with this thing here. So P4 could also be written as P0 times P times P times P times P. You see? This was that's 0. So we multiply every time. So this was when I replace it, you introduce 1p, you replace this one, you introduce another p. So the good thing about matrix multiplication is that it's not commutative, but it has the associative, it's associative. Instead of, so I can put the parentheses like this, which means that P4 could be found by P0, P to the 4, which was the thing that I told you we could use matrix power to compute these 4-step transition probabilities. So 0 plus 4, I go 4 steps from time 0. So you take the 4th power of your transition probability matrix, which gives you 4-step transition probability. So it's derived from here. So let's go back to the slides. Okay, so the state distribution is that row vector, which is basically the probability mass function. It tells our belief at this random variable, the distribution of our belief over the states at time t. Usually P0 is the initial distribution at time 0 that is given to us. For example, when we say Monday is rainy, is it also a state distribution when I say Monday is rainy? Yes, it's basically saying that P0 is equal to 1, 0. Okay, so this is, you can indicate your belief that Monday is rainy by setting up your state distribution as 1, 0. It's 100%. With 1.0 probability it's rainy, with 0.0 probability it's sunny. That's basically saying P0 is rainy. And the entire distribution of the Markov chain, okay, if you have a homogeneous Markov chain, if you know the transition, 1-step transition probabilities, and if you know P0, you can answer any question at any time point. Those are the only 2 things that you need for a homogeneous Markov chain. What is the initial state distribution? And what is the 1-step transition probabilities? What are the 1-step transition probabilities? So given Pij and the initial state distribution, you can answer any question about any time point. So the entire distribution of the Markov chain is determined with these 2 things. So yeah, things we can compute from these 2 things, many things. And one thing we're going to see is something interesting. So I mentioned this, we can compute where the H-step transition probabilities. What is the probability to go from this state to this state in H steps by taking the successive, the powers of this capital P matrix that shows these Pijs. We can also figure out what the state distribution is going to be at time H, given these 2 things. Here is something that is interesting. What will happen when we take the limit of this time step to infinity? What will happen if I continue doing these transitions again and again and again? What is the long-term forecast when H becomes infinity? What is at infinity? What is the probability to become rainy at infinity? What is the probability to become sunny at infinity? The limit can be computed by solving a system of linear equations, actually. You're going to see that. So the problem that we're trying to solve, let me write it here, is this. I need to find some, let's call it steady state. This is called the steady state distribution. Okay, steady state. Since there's a subscript to it, I understand that it's the state distribution. In steady state distribution, what will happen is this. It's steady state, it means it doesn't change, which means that if you go from steady state if you multiply it with P, your transition probabilities, you're going to get the same thing. It doesn't change. Okay, so it converges to something. This is what we're looking for at the limit. Not all Markov chains have a defined limit. Uh, we are going to see another term for that. Regular Markov chains. Regular Markov chains have steady states, but if it has a steady state, this condition should hold. For example, let's try to figure out the steady state for this weather condition. Okay, here in the steady state, we can find the steady state by just looking at these one-step transition probabilities. And I know that this is a regular Markov chain because it was like this, right? Let me get the numbers correct. Yeah, 6437. So given this matrix, the regular Markov chains are Markov chains in such a way that if the this distributions from one state to another, the h-step distribution matrix has all non-zero entries for some h. So if there exists an h for which p to the h contains all non-zero entries, if p to the h has all of the entries which are greater than 0 for some h, for this one, for example, for h is equal to 1, I have that. So that's regular. But I may have things, for example, the one-step transition probabilities may be given to you such that certain transition probabilities may be 0. It doesn't mean that it's the Markov chain is non-regular. But if there exists some h in which we will have all non-zero values, such a Markov chain is called a regular Markov chain, and regular Markov chains have always they converge to some probability transition at infinity. Okay, but certain chains do not have any. They are not regular. Let me show you such transition probabilities. For example, this 0, 1, 1, 0. Look at this. So this doesn't converge. If you take the second power of this, it will be maybe, is it going to be the same? I'm not sure. But what it's saying is that if you're at time t, if you're in this state, in the next time step, you go to this step times this state. If you're at this state in the next time step, oh, actually, yeah, if you're here, you go to here. So if you have something like this, 1.0, and no self-transitions. Self-transitions are all 0. Okay, imagine a Markov chain like this. So it will never converge because at, for example, if at even time steps, I will be at one of these states given the initial state. If, for example, the initial state is state 1 and this is state 2, okay, and if at p0 I'm at state 1, at all even numbered time points I will be at state 1, and odd numbered ones I will be at state 2. So it will never converge when h goes to infinity. And if you take successive powers of this, there will always be some 0 entries in this thing. So therefore this is not a regular Markov chain. But ours here is a regular Markov chain. And before we, in the last 5 minutes, I will try to find the steady state distribution of this one. So as time goes to infinity, what will be the weather condition is going to be like it. So it's like an overall general statistics about this town. Okay. So the steady state probabilities, let's call them pi, the probabilities pi rainy and pi sunny. I don't, these are unknown. I want to find them out. So the result is this one is, if you multiply this pi s, if you multiply it with this matrix, 0.6, 0.4, you should get the same thing, right? So let's see what this multiplication gives me. It tells me that pi r 0.6 times pi Rayleigh plus 0.3 times pi Sunny is equal to pi Rayleigh, right? I mean, multiply these two things, it should give you this value. I get one equation by multiplying this row with this column, 0.6, 0.3, gives you pi Rayleigh. Now let's look at the other thing. 0.4 pi r plus, oh no, multiply, yeah, 0, so let me, yeah, and 0.7 pi s should give you pi s. So it seems I have two equations, two unknowns, system of linear equations. Like it seems I can solve this, but actually there are infinitely many solutions. If you try to solve this, you're going to see that they are linearly dependent on each other. So well, what does this tell me? It tells me that 0.3 pi s is equal to 0.4 pi r, right? This is what the first equation tells me. If I put this one to the other, 1 minus 0.6 gives me 0.4. What does this tell me? It tells me 0. This should be 0.7, right? I multiplied it incorrectly. Yeah. So what does this tells me? This tells me that 0.4 pi r is equal to 0.3 pi s. Okay, these two equations, they're basically the same equation. They give me exactly the same thing. 0.2 pi r is equal to 0.2 pi s. So can I not find the steady state of this? Is there any other equation that I can use to find pi r and pi s, which are independent from these two? I mean, they are the same equations basically. Can you figure out from this, can you find pi r and pi s? What is the probability to be Rayleigh at the steady state? So these pi's are nothing but just variables that I defined. They're probabilities. I could have gave them small names p, but I just used the same convention, same variable naming in the book. So is there any other equation that relate pi r and pi s? Does this state distribution has another property that we know, being a probability mass function? Any ideas? Maybe it's too obvious, that's why. Yeah, exactly. They add up to 1. So there's another equation that I have. Pi r plus pi s is equal to 1. Okay, so by using these two things, which are independent from them, I can actually compute the steady state distribution. Let's do that in the next slide, and then I'm going to conclude today's lecture. So 0.4 pi r is equal to 0.3 pi s. So if pi r plus pi s is equal to 1, I can replace this pi s with pi r plus 0.4 pi r divided by 0.3. Okay, this is what pi s is. So just put 0.3 over here. So this one is equal to 1. So which gives me 0.7 pi r is equal to 0.3, which gives me pi r is equal to 0.3 divided by 0.7, whatever it is. Let me just look at my calculator here. 0.3 divided by 0.7, it's 0.42, so 86. So pi r is equal to 0.4286. So, and pi s is going to be equal to 1 minus that value. So we have figured out, sorry, this is 6, we have figured out in the long term This town is mostly sunny, not mostly. It's like around about 60% sunny and 40% rainy on the long term. Okay, in the long term. So this is how we are going to find steady state distributions by solving these um, system of linear equations, and by also using the fact that the summation of those probabilities is one. So and we could have also found this with a simulation, for example. We could have tried maybe in a number of, we could try in a while loop. If you have a lot of states, what you could do is, instead of trying to solve this equation, you could simulate this convergence by continuously multiplying the previous time point with the new one, previous time point with the new one. If you like the, for example, so this is what I'm trying to say. So you can compute t plus 1 from pt by multiplying it with the transition probability, one-step transition probabilities. If the difference between pt plus 1 and pt, if you may look at, for example, the Euclidean distance between these two vectors, or the Manhattan distance between these two vectors, you may take the absolute difference between these two vectors. If it's, for example, it's smaller than some epsilon, you may consider this to be converged, and that may be your state distribution at the limit. So it's also possible to solve the steady state distribution with some kind of a simulation by continuously multiplying it and in a while loop until, and continue that while loop until two successive state distributions like pt and pt plus 1, the difference between them is less than some value. All right. So I will stop recording now. That's it from me for today. Do you have any questions before I stop? All right. I will continue with the remainder of this chapter on Thursday. That's it from me for today.